Okay, this example is calculating the electric field at point P over an infinite plane of charge. This is a very interesting example, and it brings up a surprising result at the end. In this diagram, electric charge is distributed uniformly over the entire plane. We call the charge per unit area the surface charge density. We denote it by sigma. What is the electric field at point P at a distance a above the plane? Now the first thing we're going to do is assume for the moment that sigma is positive. So on this plane here we're going to divide the charge into narrow strips. So you can see there's a narrow strip. In fact, I've got a better argument on the other. I've got a better diagram on the next page, but I've just put a small one here. I hope it's clear. But basically that's the y-axis. This is the x-axis, and there's the z-axis going here. You can imagine that's sort of coming out of the plane, if you like, coming out of the paper, if you like, but obviously to draw it, I've drawn it at an angle here. Okay, the point is in the middle here. We've also designated the distance between the strip of charge here to the point P as r, and the distance up along the z-axis is a. That's the distance from the point P to the plane. The actual perpendicular distance is the distance a, and this little strip that we're going to look at to calculate this problem, this little strip of charge here all the way along y, distance from P of r. If we divide the charge into narrow strips of width dx, so there's the width dx, parallel to the y-axis, you can see this strip's parallel to the y-axis. Each strip can be considered a line charge, and we can then use the result of the previous example. The area of a portion of a strip of length L is L dx. So this, if we think of this whole length here as L, then the area of this strip will obviously be L times the width, yeah? So it's width times height, if you like. So that gives us the area of this whole strip. And the charge of this whole strip then is obviously we multiply the charge per unit area times the area, which obviously if you cancel the units you end up with charge then. So the little bit of charge, because obviously that's this dx is going to be really small, so the whole length of this line is going to have a really small piece of charge, and that piece of charge is going to be the sigma, the charge per unit area, times the area. All we do then is we take that equation here, divide through by L on both sides, and we've got the lambda that we're going to use from the line equation on the last example, yeah? So that gives us lambda equals dq by L, and obviously with that means we've got the charge per unit area on this side with the dx. So basically lambda equals charge per unit area times dx, so that's going to come in useful. We're going to use this equation from the last example here, is this one here, lambda over 2 pi epsilon naught, and obviously we're just going to replace the lambda here with the unit charge per unit area sigma times dx. So now we've got the magnitude of this electric field at point P. Go on to the next sheet because the diagram's a bit clearer, and we'll carry on. Now there's a component in the x direction, which that represents DEX, and there's a component in the z direction that represents DEZ. So what we're going to do is resolve it into components, okay? Also, this angle here between the line that's joining P and the strip, this angle is the same as this angle up here. You can see that by similar triangles, yeah? This angle equals that angle, therefore that's a 90 degree there, that's 90 degree, therefore that angle equals that angle. The contribution of the electric field in the x direction at this point P, if you can imagine this, there's for every strip on the plus x there's going to be a strip on the minus x, and the electric field, they're going to cancel, yeah? You can see that the contribution of electric field in the x direction, in that direction, is going to be cancelled by the electric field on the same strip in that direction. The resultant field at P is therefore in the z direction perpendicular to the sheet of charge. So the only force we're going to be considering then is this component of the force here, because that's the only one that's going to contribute, yeah? So that's what we've got to calculate, this DEZ. We know what the magnitude of this is. that is from the line charge equation, lambda over 2 pi epsilon naught r. So we've got the magnitude, and we also do that substitution for lambda, so we got sigma dx. Okay, so that's what we're going to use here. Now the other thing about the ratios in a triangle, we know that the sine of an angle gives us the ratio of the opposite divided by the hypotenuse. Yeah, so if we're looking at that, that's this, which is the dEz, divided by the magnitude of dE, will give us sine theta. That's the ratio. So that's what we've got here. Okay, so we can write that down because that's true. With that, we can rearrange that. We know the magnitude of dE, and we'll get the sine theta in a minute. Yeah, so that gives us the size of dEz. Okay, so that's good. We've got that. Right. So the next step here is, let's see where we are now. So what we're going to do now, of course, is we need to replace the dE. Now we know what the dE is. It's this equation here. Okay. Once we've replaced the lambda with sigma dx, we've got this part here. So we're going to take all of that and place it in there. And when we do that, we end up with this. So you can do that. It's just a bit of algebra. So when you do that, you end up with this. Now at this point, so we've got the little bit of Ez, okay, for the little bit of dx. So for this little bit of dx, we've got a little bit, we found this little bit of Ez in that direction. But what we want to do, of course, we want to add together all the contributions of these little dz's all the way along, all the way through the plane by integrating from here, from plus x equals plus infinity to x equals minus infinity. So that's what we're going to do. To find total z component of E, in other words, we won't have a delta anymore, it'll just be Ez. We integrate this equation here, so we've got it set up now to integrate, as you can see, from x equals minus infinity to x equals plus infinity. So if we just put the integral sign in, and we'll take the d away here, we end up with E, the integral over dEz. Now we know that dEz is this equation, so we plug that in. We'll pull out all the constants, so sigma 2 pi epsilon naught. We'll put our limits of integration here, plus infinity to minus infinity. And all we're left with then, once we've pulled out these constants, is sine theta over r. Now, sine theta is also a ratio. Now, as I get, because of similar triangles, remember sine theta is a ratio, yeah? So that's going to be useful, because we know here that, again, looking at this triangle now, sine theta equals the opposite divided by hypotenuse, so it's a over r. So also the ratio of sine theta is a over r, so we can put a over r, we can use that, and if we place that back into here, so you can think, if you place that a over r here, you're going to get a over r squared, so that now can be written as a over r squared. But the other interesting thing is r squared equals a squared at x squared. So I mean, these substitutions are not obvious, so you wouldn't know, so it's better just to go through them and see how this equation ends up the way it does, yeah, because you know, it's not obvious that you're going to do all this substitution. So r squared equals a squared at x squared. You can see that's true. You can see that the hypotenuse is a right angled triangle, so r squared equals a squared at x squared. So we can write that. So that means our r squared, which I said underneath here, when we got a over r squared, we can replace that, pull the a outside, so we end up with this. We've pulled the a outside and we've placed the r squared as a squared at x squared. Now, the reason this substitution is done is because, the main reason is when you get the integral in this form, there's a standard lookup for that. Okay, we're going to use this book again, and I mean, this, if you've got a book similar to this with your equations, quite useful, these ring binder ones, really nice. Well, so obviously here's what we've got here. We can see we've got some chart of standard integrals here. Well, that's good, because now look, we've got it in this form here, yeah. So you'll just know that if you ever see that, then you know that the integral of that is this. Okay, so either you know it or you can look it up in a book. And to prove that integral, that standard integral, that's a huge lot of derivation itself. But you don't need to do it. It's like it's well proven. Yes, you just accept that really. So that integral then, we know by looking up in our lookup table of integrals, is this. Or you could just plug that into Wolfram Alpha if you like, you know, you can get the answer that way. But anyway, we won't, we'll put it in here. And now we've solved our integral, and now we're just going to plug in the limits of integration. So we've done all the hard work now, we've solved the integral, we're going to put the limits of integration in here, okay? Now the thing is to think about an arctan. If you put a really large number in x here, now you know that tan is the opposite divided by adjacent, yeah? So x divided by a, yeah? So obviously if you're going to have a very, very large x, you can see that the angle, this angle is going to go up and up, it's going to get larger and larger, and it's going to get to a point where it can get no further, and it'll be pi over 2. Okay, so if you stick into your calculator arctan over a massive number, you're going to get pi by 2. I guarantee you'll get it. You'll get a number, and if you multiply it by 2, it'll come to pi, yeah, 3.14. You can try that in your calculator. When you plug in those values, you end up with this, okay? You end up with, remember, in an integral, you're doing that minus whatever the lower integral is, and in this case it's a minus, so that becomes a plus. So when you do that, it's really easy. You get pi over 2a plus pi over 2a. Well, that's 2 pi over a. Well, obviously the 2's are going to cancel, and when you bring it all out, the a's are going to cancel, and everything cancels basically, and you end up with sigma over 2 epsilon naught. Now that is interesting. This is this whole derivation here has proved that if you have a point above an infinite plane, doesn't matter how far the point is, the field that it fills is completely independent of the distance. Now that's not obvious at all, and it's really surprising, and it, you know, there's no I can't think of a good explanation why really, but this has proved it, and it's been proven in experiment with a really large infinite plane, that no matter where you are above an infinite plane, and you know, if you've got a very, very large plane of charge, the distance doesn't really matter where you are. You're going to feel the same field, okay? And the field is going to be whatever the charge density of the plane is, which is the sigma, divided by 2 epsilon naught. So that is fascinating.